In this module, we will consider potential energy. Let's consider the work done on an object by both gravity and by friction as the object moves along various paths. First, let's consider an object moving on a horizontal surface under the influence of a kinetic frictional force of constant magnitude. The direction of the frictional force is in the opposite direction of the motion, so the work done by friction on the object will always be negative. That is, the work done by friction can be written as minus the magnitude of the kinetic friction times the distance traveled by the object. Now let's consider an object of mass m moving in a vertical plane. The force of gravity is in the downward direction, so we can write this as minus mg j hat. Assume the object moves upward at some angle theta relative to the horizontal and travels some distance d. In order for us to calculate the work done on the particle by gravity, we need to know the angle between the displacement vector and the direction of the force. Using this angle, we can compute the work as mgd cosine of this angle, which turns out to be minus mgd times the sine of the angle theta, which is the angle of the trajectory relative to the horizontal. Now, d sine theta turns out to simply be the vertical change in the position of the particle. So, more simply, we could write that the work done by gravity is minus mgh. It depends only on the height gained by the object and is completely independent of any horizontal motion of the object. We see then that an object with a net increase in its vertical position has negative work done on it by gravity. Similarly, an object with a net decrease in its vertical position has positive work done on it by gravity. So we can write the work done by gravity on a particle of mass m as minus m times g times the quantity, the final y position minus the initial y position. That is, the net work done by gravity on an object is proportional to the net change in the object's vertical position. In summary, we see that friction always does negative work on an object, and the work is proportional to the total distance traveled by the object. Gravity, on the other hand, can do both positive and negative work on an object, and the work is proportional to the net change in the object's vertical position. So, given fixed starting and ending positions, the work done by friction depends on the path taken between start and end, while the work done by gravity does not. A force is said to be conservative if the work it does on an object moving between 2 points is independent of the path and depends only on the initial and final locations of the object. So gravity is a conservative force, while friction is not a conservative force. An equally valid alternate definition for a conservative force is to say that a force is conservative if the work it does on an object moving on every closed path is zero. Because the work done by conservative forces only depends on the initial and final positions of the object, it can transfer energy to and potentially recover energy from an object based only on its change in position. The energy that is transferred to and recovered from an object by a conservative force is called potential energy. The change in the potential energy of an object is equal to the negative of the work done on the object by the conservative force. So we can write the work as minus the change in the potential energy. That is, the potential energy at the initial position minus the potential energy at the final position. The potential energy due to the gravitational force on a mass m depends only on the change in the vertical position. So to calculate the change in the gravitational potential energy, we calculate minus the work done by gravity as the object moves along its path. Gravity, of course, is minus mg j hat, and we're going to only consider motion in the vertical direction. So our dy will be in the j hat direction. And so if we do the integral, we find the result is that the change in the gravitational potential is mg times the final y position minus the initial y position. So we can define the gravitational potential energy, u sub g of y, as mg times y minus y sub naught. Now, why are we adding in this additional term of y sub naught? Well, it turns out that only the difference in the potential energies matters. So we are free to choose the vertical position that corresponds to zero potential energy. That is, we're free to add any arbitrary constant we want to the definition of the gravitational potential energy. In this case, adding the y naught allows us to choose the height y at which the potential energy of the particle is zero, and sometimes this can be useful in working problems. Hooke's law for a spring with a spring constant K is also a conservative force, so we can calculate its potential energy. The change in the potential energy for a spring, again, is minus the work done by the spring between its initial and final positions. And if we do the integral, we wind up with 1/2 K x final minus x naught initial squared minus 1/2 K x initial minus x naught squared, where x naught is the equilibrium position of the spring. Clearly, we can define the potential energy of a spring as 1/2 K times the position minus x naught squared. We could, if we wanted to, add an arbitrary constant to the potential, but there is never any advantage to doing this. Adding a non-vanishing constant to the definition of the potential energy of the spring simply shifts the position at which the spring is said to have zero potential away from the equilibrium position. Now consider motion only in the x direction. From the definition of the change in the potential energy, with a little bit of work, we can show that the infinitesimal change in the potential energy is equal to minus the force in the x direction times the infinitesimal displacement in the x direction. Rewriting this, we see that we can compute the x component of the force as minus the derivative with respect to x of the potential energy. An analogous rule holds for the y direction. So, for example, we could compute the gravitational force by taking minus the derivative with respect to y of the gravitational potential energy. The result is minus mg. So since this is in the y direction, we recover that the gravitational force is minus mg j hat. If we consider the potential energy of a spring and take minus its x derivative, we recover exactly Hooke's law. This relationship between force and potential energy is just telling us that the force is minus the slope of the curve of potential versus position. So let's now consider potential energy diagrams. If we draw a diagram with potential energy on the vertical axis and position on the horizontal axis, and we look at the slope, then for example, where the slope is negative, we see that the force is going to be to the right. Wherever the slope is positive, the force will be towards the left. At a minimum of the potential energy, we find that the slope is zero, and therefore the force is zero. And this is what's referred to as a point of stable equilibrium. It's stable because if we were to shift the particle slightly to the left, the force would be towards the right, and if we shift the particle slightly towards the right, the force on the particle would be towards the left, and so we're always acting to push the particle back towards the equilibrium position. On the other hand, at a maximum of the potential energy, the slope is again zero, the force is again zero, and this is what is referred to as a point of unstable equilibrium, because in this case, if we push the particle slightly towards the left, now the force will try and push the object even further away, and the same is true if we push the object slightly towards the right. So what we see from all of this is that the force associated with a potential causes the object the force is acting on to seek the local minimum of the potential.